Please welcome co-founder and chief executive officer for Neo4j, Emil Eifrem.
Wow. Wow. It is fantastic to be back. To do this face-to-face after 4 years now? Hang on. Wait for it. No. I need you to smile and cheer and look. I can see you. Come on. Yeah, that's right. Fantastic. How amazing is this? 3D. I remember it vaguely from before the pandemic. Many of you showed up at the welcome reception yesterday. I thought the vibe was absolutely fantastic. It was amazing to be able to meet in 3D. A little bit weird. I was trying to look down to the right, to the Zoom window and see who I'm speaking with, but realized that at a conference you should look, it's here, it's the badge there, right? We're all wearing pants now. I'm thankful for that. Appreciate that a lot. But overall, just so amazing to be able to do this, face to face, in a real room with real people. So I see a lot of old friends here in the audience. In fact, how many has been at the GraphConnect ever before? Raise your hand. Wow, fantastic. How many was here at GraphConnect 2018? How many was here at the GraphConnect before 2018? How many was here at the GraphConnect in 2020? Trick question. Good, you're awake. I like it. The coffee is kicking in. Fantastic. So, my name is Emil. It's on the big screen out there. And some of you who've been here before, the 2018 and before crowd, you've heard me mention this before, but I want to help the world to make sense of data. That's our mission here at Neo4j, help the world to make sense of data. Through graphs, we think that's at least the smartest way we've been able to figure out in order to make sense of data is through graphs. I have 3 daughters, 10, 6, and 4. They're watching the live stream. Hey, daughters, how's it going? Go to bed. It's getting late in Sweden. And I think when they were born, when anyone is born, you know a few concepts, right? You know mom, temperature, hot and cold, boobs, right? The essentials to get by, right? If you're an hour old or something like this. And then, as you learn more about the world, you learn a new concept by relating it to previously known concept. That person over there, he's kind of like mom. Let's call him dad, right? And so that as they're crawling out into the world and walking out into the world, They're building up their graph of known concept, and they're adding to that by taking the unknown concepts, relating them to the known concepts, which builds up their understanding of the world. Relationships are fundamental, I believe, in how the human brain works, physically, anatomically, of course, neurons and synapses, but also conceptually. And that's fundamentally, of course, what graphs are about. So these next 2 days, well, I guess 3 days, including yesterday for those of you who are here for the trainings, we're going to talk about graphs, and we're going to share our own stories about graphs. And you're going to hear from people who are expert users who've been using graph technology for a month or a year or 5 years, and they're going to tell their stories, how graphs help them make sense of their data. And you're going to hear from the people who are actually inventing this, who are building the technology, who are building the latest and greatest, of which we will talk about later on today. And you can learn from them how you can use that technology to help make sense of your own data. So that's kind of the framing of these next couple of days. But first, we're going to start with the story of graphs in and of itself. And graph databases really started coming into popularity about 10 years ago. And it's been quite an astounding decade. There's a site called DB Engines that tracks popularity and usage of databases. And you can see here on the screen that graph databases has been the fastest growing category in all of data management for most of the previous decade. And as I think back to early on, 10 plus years ago when we invented the technology, and I look at today, it's been downloaded over 100 million times. And there's an active community of more than 250,000 people that are actively using Neo4j. And of course, all of you here in this room are part of that community too. And in large part, thanks to this community, Neo4j has been used in some of the biggest and most amazing companies in the world, in a wide range of industries. 8 of the 10 biggest insurance companies in the world rely on Neo4j. 7 of the 10 biggest retailers. Every single one of the 20 biggest banks in all of North America use Neo4j. And in fact, over 75% of the Fortune 100 today use Neo4j. So we're very fortunate to see the depth of adoption of graph technologies over the past decade. In fact, the traction and the interest and the usage of graph technologies is so huge that Gartner is now predicting that by 2025, graph technologies are going to be used in 80% of all data and analytics innovation. That's a very stark quote. 80% of all innovation in data and analytics, which arguably is a large share of all innovation at all, right, is going to be based on graph technologies. So huge interest, huge usage, a lot of value that people are deriving for this. That leads to a vibrant and growing market. And there's a lot of companies who would look at this and they would say, competition, oh no. And here at Neo4j, we're wired a little bit differently. Because from day one, we started out with what people think of and call a category creation strategy. So this means that we initially coined the term graph database. We put those 2 words together. And then we were very focused on evangelizing the concept of using relationships to make sense of your data. And yes, fantastic if you use one of our products. We love that, of course, right? But really, the more important thing is that people stop walking around in this highly connected physical 3D world that we talked about. Stop doing that, but then dropping those relationships on the floor when we digitalize that world. Because that's ultimately what we've been doing for 3-4 decades in computers. So if 10 years ago in 2012, I would have sat down and I thought, what does success look like, right? It would actually look very much like this, that we have a bunch of competitors, big companies and small companies, that are all participating in the graph market, and we're the clear leader. That is actually what success looks like when you do category creation. And that vibrant, growing market is ultimately best for all of us here in this room. So what are people using graph technologies for today then, right? So there's a wide variety of use cases. Fundamentally, graph technology is horizontal. It's kind of like it's the 80s we're at SQL Connect. No, that's probably not the name of it, but whatever, like a conference about SQL databases. Tabular Connect, I don't know. And we're talking about the use cases for the relational database. And there will be early use cases, but fundamentally it's a horizontal technology. And the same is true for graph databases. But what are then the early adopter use cases? And here's a snapshot of them. And so what we have here in this slide is you have an inner circle of what I think of as kind of core data sets. These could be things like employees, suppliers, transactions, customers, things like that. And then in the outer ring, in the outer circle, you have some core use cases, the most popular use cases derived off of that data. And what we see happening is that people adopt Neo4j for, let's say, fraud detection, as an example, right? And so they work off of the transaction data, the commercial transaction of that company. And they start doing that, and they use Neo4j to capture fraud rings, right? That's a highly connected problem. And so they get a lot of value of that. And then after a while, they realize that, wait, I already have the commercial transactions in here. What if I add my product hierarchy, and then I can use that to do a recommendation? In fact, I can do that in real time. That's really powerful. So then they add a second use case. And then they realize, wait, OK, so I have my product hierarchy. I can launch a digital twin with this that I mash up with my supply chain. All of a sudden, my recommendations become much smarter because then I'm now only going to recommend things that I can actually supply and ultimately deliver to the customer. And then the supply chain is in there, and all of a sudden you can start doing predictions on your supply chain to figure out if there's going to be any disruptions or things like that, right? And so there's a network effect in use cases in graph databases that we didn't really see in the early days because it was just too early. People adopted us for one use case, and that was enough, right? And now we're starting to see this explosion, this breadth of use cases, centered in many cases around these, but in no way is this an exhaustive list. So that's kind of the summary from a use case perspective, but a great example of starting with a single use case and then branching out to more. We're going to talk about now. And you're not going to hear it from me, you're going to hear it from them themselves. And this is from a company called CSX Technology, which I think many of you here in the audience is probably familiar with. But they're in CSX, they're responsible for monitoring and tracking a very complex railroad logistics system across the entire United States. And here to tell you on the screen, virtually, how they do that with graphs is Dave Rich. So roll the tape.
As you can imagine, a railroad, we're extremely asset heavy, lots of assets that we're hauling day in and day out. And the relationship between those assets are just so important to our core business. And everything is just so fluid. If you think about the journey and the life cycle of a rail car that may start at a customer, it works through a myriad of networks to get to what we call our yards. If you think about trucking and intermodal, those go to our terminals. And then if you think about kind of the graph database itself, how it's a node and edge, the rail network it's almost symbolic of that itself. If you think about all rail lines, those are the edges, and each of our yards and terminals are those nodes as far as how you transpire through the network and how you send your goods and services. So it's extremely complex. Some of the things that we have challenges for, if there's disruptions to the network, think natural disasters and those sorts of things, you can't just fly around it and divert or take another road. So the complexities that we go through on the railroad are quite unique. Graph is very well suited for CSX and our railroad. Like we talked about before, our network is almost a mirror image if you think about the technology of graph itself, again, that node and edge. So it really helps us efficiently track and report and visualize hundreds of thousands of assets and the interrelationships over time and how they transpire. In our Neo4j instance, we have 24,000 locomotives that at some point have traversed through our database, 3,500 of which are CSX. So that implies that we have a heavy partnership with other railroads, short lines that we work with day in and day out to deliver those goods and services to the US. 6,700 train crew, 1,600 trains per day are captured in our Neo4j system, over 250,000 rail cars, and over 1,100 stations throughout the CSX network. So if you think about how complicated the relationships are between all of those different assets and all of the different events that are happening over time, Graph is really well suited for us to kind of help understand the relationships and the events that are occurring day in and day out from a logistics standpoint on the railroad. Technology is absolutely critical to get a better understanding of how things are interconnected. I mean, heck, look at baby formula. And what happened there. So it's a lack of understanding and how do we react it and seeing the data earlier and being able to respond. We wouldn't be sending shipments from Germany over to the United States today to be getting formula. We would see it in advance. We'd have these systems in front of us to be able to respond to it. So those are examples of how you can lean into technology to really help you gain those insights and get predictive. And that's, I think, a big part of Graph too, is that how do we not just look at what's happened in the past, but leverage it to kind of help us predict into the future what we might be able to see, looking at those trends and information to go there. So it's huge. It's absolutely huge for logistics.
All right. I love that. Railroads are a graph. Great insights. There's a lot of stuff in the physical world that once you start looking at it, it's actually deeply connected, right? And we talked about the human brain, we talked about biology, but supply chain, product hierarchies, and of course railroads as well. And we can even think about it, people talk about railroad networks. And whenever people use the term networks, that's typically a good clue that graphs are involved. And we have the saying internally at Neo4j where we talk about graphs are everywhere, right? And this is, I think, a great example of that. So one of the amazing things about being here at GraphConnect, and I talked a little bit about that early on, is that you don't have to take it from me trying to summarize across our entire thousands, if not tens of thousands, if possibly even hundreds of thousands of Neo4j deployments. What are the core use cases? But there's a number of people that are talking here today over the next 48 hours. And you have them here on the screen. This is a sample. But a number of current, present, summer 2022 use cases for graph databases. You have CSX with their digital twin, which you heard the high-level story of here, but then there's a wide variety of other use cases. So I urge you to look them up, add them to your session on your mobile app, and if you're interested in a particular use case, go ahead, check it out, hear it from them. So switching gear a little bit. I've been reflecting, it's the first time we're back after the pandemic, and I was going even earlier back and thinking about the amount of progress we've made, starting from, going all the way back to when Neo4j was just an idea on a napkin, and the advancements, the progress we've made since then is just astounding. But even going back to last GraphConnect in 2018, we were a couple hundred people then. You could fit us all in this room. And today, we're over 800 people globally and growing fast. And 300 of them are engineers, which work every day to create the best graph technology on the planet. And so I was reflecting on what are the high-order bits? What are the kind of top things that I think have been material since we last met here at GraphConnect in 2018? And this has been a painful journey. It's a little bit like those 3 daughters that I talked about before. It's choosing your favorite child, which I don't have a favorite child. I love you all equally. And it's the same with many of these amazing features that we built over the last several years. But I want to call out three particular things. The first one is Neo4j Aura, right? And this is probably not a surprise to anyone here, but this is our cloud database as a service offering. And it's a really important piece of technology, shifting us into a cloud-first company, where over time we're shipping our features first in Aura, actually, and then subsequently into the self-managed versions. And Aura has a wide spectrum of offerings. It starts with a free forever tier, Aura DB free, where you can just sign up. I hope many of you have done that. In fact, raise of hand, who here has signed up for Aura DB free? All right, probably 40%. So let's try this. Who here has not signed up for Aura DB free? It's like 10%. I think I'm now going to switch into like a Venn diagram lecture. It can't be like if it's not signed up, that should be 100%. But at least for the 10% who hasn't signed up, the 10%, go to neo4j.com/Aura, sign up. It's free forever, up to 50,000 nodes, 175,000 relationships. Just get going, completely managed in the cloud, all that good stuff, right? So that kind of starts there. And then we have Aura Professional, which is a page, swipe your credit card, self-service, $65 per month type offering that you can run mission-critical production workloads off of, all the way to AuraDB Enterprise, which is the kind of the big brother amongst the Aura tiers, which is used for those mission-critical enterprise-wide production deployments. And it's super popular. I'll give you a couple of data points. Over 5,000 people actually sign up for AuraDB Free every week. Every week, 5,000 people. That's pretty amazing. That's one example. Second example, AuraDB Professional runs over 10 billion queries every month. 10 billion queries. That's an astounding number. And AuraDB Enterprise is already today, it was launched just over a year ago, and it's already trusted by some of the biggest companies on the planet to do really mission-critical, important use cases. So that's the first Aura. The second one is Neo4j Fabric and Graph Native Sharding. And so what this one is that we launched a sharding technology in Neo4j 4.0 initially, and then we've evolved it since then, called Fabric. And this is what's called graph native sharding. So big picture you can think of, there are two broad ways that people try to do sharding of graphs, which is a really hard problem. One way is you take your data and you shard it in the tried, true, and proven way that people have been able to shard data sets for at least 10, 20, maybe 20 years, but probably more like 10 years, right? In products like DynamoDB, and even in products like MySQL, where actually the term was initially coined sharding, which is you split it up and you spread it evenly across your entire cluster amongst all your shards, right? That's one approach. That approach does not work for graphs, right? It's a spray and pray approach. The entire secret with sharding graphs is that you need to be aware and mindful of the shape of the graph, because otherwise, as you're traversing the graph, you end up hopping across the network, right? And you want to stay as much as possible on one shard, right? So what we've built instead is what's called graph native sharding. And what this one is that you invest ahead of time in data modeling to give your cues to the engine that, you know what, this one over here will be tightly connected. This one over here, not so much. You give it some cue to the engine. After that, you get absolutely magical properties. You get unbounded scale. So what this means is that if you have one machine that supports like a billion nodes and relationships, if you had two machines, you're going to get 200 billion. You had three machines, 300 billion, right? So unbounded scale. You get linear write throughput. So in other words, if you have one machine and you support X transactions, right? You had two machines, you support 2X. Three machines, 3X, right? So linear write throughput. And then, most importantly, and think about amongst yourselves, why are you using graph database? It's very likely, at least one of the reasons, is query performance. And then, so the third magical property is that you get constant read performance. Constant read performance. So in other words, if a query responds in Y milliseconds when you have one shard, it responds in Y milliseconds when you have 100 shards. And so we honestly probably didn't do a great job of getting the word out about the magic of Fabric when we first built it. Maybe because we weren't able to have these amazing face-to-face gatherings, I don't know. But so what we did about a year ago for Nodes 2021, which is our online-only developer and data scientist conference, we pulled together a demo. And that demo was really, really exciting. ABK, Andreas Kolliger, who's actually here today, and a big team inside of Neo4j worked on putting together a demo of a social network which had people and then posts, and those posts could nest, and you had tags in your forums, and you could subscribe to tags. So you can feel that that's a fairly connected data set. And they built this out with about 10 billion-ish nodes and relationships. I think initially it was 19 billion, but let's call it 10-ish billion, running across 10 shards. And then they ran some really convoluted, hard, and messy queries. Things like, give me all the people who are following this tags and this tag and the most recent post in that, for that tag. It's like you have to go to all the shards and you have to traverse down several hops. So it's like, it's not a simple get and put thing. It's like a real graph query. Ran 4 or 5 of those. And with this 10-ish billion, whatever, 19 billion nodes and relationship, it's hard to see probably here, it had a latency of less than 20 milliseconds, right? Across 10 shards, 19 billion nodes and relationships. But then they did something really interesting. They 10x that. And they said, you know what? We're going to run this across 100 shards, 100 billion-ish nodes and relationships. And at that size, the latency was still less than 20 milliseconds. And that's pretty cool. But then, not to be outdone, they said, you know what? We're going to 10x it again. And so then this thing, social network, ran on over 1,000 shards, over 1 trillion nodes and relationships, and still with latencies of less than 20 milliseconds. That's pretty amazing. And some of these queries were really, really gnarly. We're talking graph global queries touching all 1,000 shards before they could return, right? And still in less than 20 milliseconds. Graph native sharding. Magical. So that's the second one. The third one is graph data science. And so what this one is, we grew up with a product that was targeted to developers building applications. Over time, we in the industry at large have realized that, you know what? Yes, the graph data model is amazing for your application, for expressing your application, for performance in that application, all that good stuff. You know what? Relationships are also really predictive signal into your machine learning. And what if we can take our database and adapt it for data scientists so that they can use that as a way to build their models and use history to predict the future? And so that is what graph data science is. It's a really, really hot area. It's a huge driver of growth for the graph space in general and Neo4j in particular. And we are only just getting started on this one. You're going to see some really exciting things later on in just a few minutes in the graph data science area. And in fact, Gartner is saying that by 2025, graph-based machine learning models will replace 60% of all existing traditional models. So just think about that. Think about how much of your life is relying on machine learning today. It's like almost impossible to do anything on a phone or anything in the cloud today without machine learning being a part of that. And 60% of those will be replaced by graph-based machine learning models. But it's not just a future thing. It's been out for GA for 2 years. And it has a really wide depth of real big company enterprise adoption using Neo4j GDS, graph data science, already today. So that's the third one. Aura is the first one. Sharding, graph native sharding, trillion relationships was the second one, and then graph data science is the third one. But as I try to kind of synthesize and what actually happened, what happened over these last 2-3 years, really the big picture that's emerging to me is that we've changed as a company. We grew up as a database company, and the database is the heart of what we do, and it's a really valuable thing. But we're not just a database company anymore. It truly has become a platform. We have the database serving up operational workloads for, again, developers building applications, but we also have a graph data science platform that uses relationships as a predictive signal into their machine learning. We have a rich set of tooling wrapped around this, be it developer tooling like Neo4j browser, which probably, if I asked, probably everyone would raise their hand if that they're using Neo4j browser, and desktop. You have ops tooling, which we'll talk a little bit about later today, and a rich set of connectors that make it easy to get data into Neo4j and out of Neo4j with common systems that you're using today to store other data sets. And all of this is served up in the cloud through Aura. We've moved from a graph database company to a graph platform company. Cool. Shifting gears away from technology to the impact that the technology has on the world. So there's a lot of things that I love about my job, and this is a little bit akin to the choosing your favorite child, but honestly, if I had to choose one thing that inspires me the most, it is this. It is seeing the transformative power of graphs in domains where that truly move humanity, move the planet forward. And there's a lot of that we can talk about, but I've chosen two particular examples that I want to spend a little bit more time on. The first one is the ICIJ, the International Consortium of Investigative Journalists, which some of you will remember because they did the Panama Papers and subsequently the Pandora Papers. And here to tell us more about that on video is Amelia from ICIJ. So please roll the tape.
The Pandora Papers was a global investigation coordinated by the International Consortium of Investigative Journalists. For nearly 2 years, more than 600 journalists in 117 countries and territories worked together on this project. The Pandora Papers is based on more than 11.9 million records, 2.94 terabytes of information, and they come from 14 offshore service providers. So for nearly 2 years, more than 600 journalists in 117 countries and territories explored these records and went outside the records to mine the information and find stories of global interest. And the investigation that took nearly 2 years revealed secret deals and hidden assets of more than 330 politicians and high-level public officials in more than 90 countries and territories. We also revealed information about secret offshore holdings of more than 130 billionaires from 45 countries, including more than 45 Russian oligarchs. That is basically a parallel system, like that offshore economy that is legal, allows to hide all these offshore structures and how this can affect actually citizens. And some of these cases were also involved with money laundering cases, big corruption scandals. It was a big offshore data tsunami, and it was very complex to handle. Once we face all that challenge of structuring the data and put it all together, we actually use graph databases to make data accessible to the whole network and make it accessible in a different way. So people could be able to explore it and get the power of the visualization allowed to explore hidden connections. So they don't need to code, they don't need to so this is for all type of journalists, technical and non-technical journalists. So basically everyone would just go and type and search for any specific name of interest and see if that name appears there, and then how many companies are linked. And then they had links to documents, so they could go and see the full document that backs up the information behind the data. So it's very powerful because it makes data accessible to everyone, but also it allows us to explore in a smart way those connections. We will continue expanding in the possibilities graph databases will give us in the analysis we do. We will also explore how graph databases can help us with some of the machine learning work we're doing to see if there are ways in which we can integrate some results that we have gotten with machine learning to represent them in graph database formats. There is a universe that can be expanded, and we are eager to explore how they can help us continue to improve the work we do with our whole network of journalists.
All right. I love to see how the ICIJ is using Neo4j to help make sense of this really, really important data. There was There was a Twitter thread published a few months ago, maybe in April, by a researcher into international tax, which sounds really exciting. But what he said, he talked about, because this is when the Russian-Ukrainian war had just begun, and there was talk about sanctions and the Russian oligarchs that Emilia mentioned here. And he said, you know what you probably don't know here in the public is that we actually know a lot more about offshore wealth and oligarchs hiding wealth today, and that we've learned so much more in the previous decade compared to previous decades. And then he listed 6 investigations that were the key reason for this. 5 of them used Neo4j. 5 of them. That's a real impact on the world. That was a little bit of a, we talked about Graph's impact on the world broadly. We talked about a little bit of my favorite tech stuff. We talked about the Graph's impact in the world. Now we're going to go deep on the technology and talk about announcements. And here to tell you about that, I'm going to introduce you to a friend of mine who almost exactly 10 years ago, 10 years and a month or so, on his 40th birthday, started at Neo4j as the first head of product. And it's 10 years later, we're all 10 years older and at least some years wiser, I think. And he's still running product for Neo4j. So please welcome to the stage, Phillip Rathle. Oh, click it.
It's so great to be here with all of you. I had no idea I was going to be outed with an age comment. I don't know how to respond to that. But it's so great to be here together, hearing about what you're doing and talking to you about product. And before I talk about what we're building in product, I'd like to tell you a little bit about how we think about how we build the product. So we have some principles where every new release comes around for the whole portfolio for various products. We look at 3 distinct ways where we can add value. One is more features, rich capabilities that let you do more. However, it's not enough to just have those capabilities. We want it to be frictionless, as easy as possible, not just for the individual thing that you're doing, but now that we've got a whole platform, many products, they all need to hang together and work coherently. And then last but not least, none of the features matter, none of the experience matters if you can't trust it to run to whatever SLA you're operating under. And this includes things like security, operability, availability, and so on and so forth. Now that you understand this, let's talk about the Neo4j Graph platform today. This is very different from when I started 10 years ago. We had just that little thing, little blue thing in the center of the database. Now we've expanded to cover graph data science. If you actually start at the top, you can see the end user touch points and applications that are supported by Neo4j. And then those are usually accessing Neo4j through an application layer, oftentimes increasingly with an AI machine learning pipeline in the middle. And now we have a rich data science capability that sits alongside the database, lots of integration to and from different data sources on the left. And on the right, you've got various CLIs, APIs, tools, user interfaces for developers, data scientists, for doing visualization, and so on. And Emil talked about Aura, and many of you have used it. Really, the point of Aura is to make it possible for you to get all the benefits of running Neo4j without having to go and do all the work of operating the platform. And we've made a lot of strides internally over the close to 3 years that we've been running Aura. In fact, last year, we flipped our development pipeline so that now new releases of functionality land in Aura first and then get packaged up periodically and delivered through the self-serve product. So all of our development, testing, quality assurance actually happens upfront together with Aura. So now you've got a rock-solid foundation of the Neo4j Graph platform that's tightly integrated into Aura. And with Aura, everything is elastic, automatic. You don't need to worry about upgrading. Everything just works. Key point here, as of last year, you can procure directly or through your marketplace provider of choice. Now, where does Aura run? As Aura's evolved, we've created multiple offerings to serve different needs. What initially launched as Aura, now AuraDB, is the transactional database offering for running applications. And here you have a free tier, you have a professional self-serve pay-as-you-go tier, and then there's an enterprise tier with more robust security, SLAs, support, and so on. Just in April, we launched Aura DS, our first graph data science offering in the cloud. And Aura DS today runs in self-start in GCP, and alongside everything on the AuraDB side, AuraDB also supports AWS today, and we're working to expand Aura to more platforms. So later this year, you'll see AuraDB Professional and Aura DS both adding support for AWS. We're already in early access with an enterprise tier of Aura DS that's expected to go live later this year. And then we've been working hard on adding support for Microsoft Azure and are planning to enter EAP later this year. Okay, I'd like to transition into scale and speed. And this is on the GDS front. So it's now been 2 years since we launched Graph Data Science. In every single release, our engineering team has been working to outdo themselves to make this faster and faster and faster. And actually, overnight US time, Swedish day, the team was running new benchmarks with the latest 2.1 version that's coming out just later this week. And here you can see a few numbers, and they're pretty astounding. So I've got a 2 billion relationship graph running PageRank in under a minute, and running my favorite graph embedding, FastRP, in under a minute and a half. A new capability that we've added recently in the last year is being able to do in-graph machine learning. So really two ways you can fit Neo4j into a machine learning pipeline. One is to run your algorithms and then feed a machine learning pipeline. Another is to actually run your machine learning operations in the graph. And this makes sense for machine learning operations that are more graphy. Two that you see here are link prediction, predicting if a relationship, when the next relationship is likely to form. Another one is node classification, so it's node labeling. What label should this node have? And here you can see, again, some really best-in-class results, a 50,000 node to 250,000 relationship graph, calculating a 512 dimension embedding, training 2 different models, picking the best model, and then giving you the results. All end to end, that whole pipeline runs in 40 seconds. If I take a step back and look at how these two things fit together, the operational database side of the world and the graph data science side of the world, there aren't many technologies that support transactions and analytics at the same time in the same platform, and there are even fewer that do that well. But there's a very high payoff if you're able to do that, because you get, by bringing those two closer together, you end up with this virtuous cycle where you have fresher data, better recommendations in your operational systems. Earlier this year with GDS 2.0 in April, we launched the ability to run graph algorithms directly inside of a cluster, and those annotations will run back to the graph and propagate across the cluster. So great new capability there. I'm going to say one thing about Neo4j 5.0, which is due out later this year in fall, which is a big improvement in clustering. We call this autonomous clustering, and the genesis for this was those of you who are running big B2B SaaS use cases where you've got thousands, tens of thousands of separate database tenants that need to be kept physically separate, operate all of those. Obviously, you're not going to run 10,000 different clusters, so we have multi-database for that. But then if you're going to have 100 databases per cluster, that's a lot of clusters to manage. Autonomous clustering takes care of that by having one ginormous cluster where you can set a replication factor for the databases. It just manages them all. You have one endpoint. Your queries figure out where to go. It's going to be great. The last thing I want to talk about on the theme of performance is getting data into and out of the graph. With graph data science, your data volumes are ever higher, and many of you have asked, is there anything we can do to make it faster to get new data into the graph? So our team went away and looked at different options, and actually they came up with something that is not only faster, but easier. So in GDS 2.1, you're going to be able to stream data in with Apache Arrow. And in our lab, we're able to get about 2 million records per second into a new database. But that wasn't enough. The team said, well, if you're running GDS, what if we just stream directly into the GDS in-memory graph? What kind of rates can we get? And that ran 10 times faster. This is going to be available later this week. And if all of this sounds crazy, then I think there's no better way to show this than with a demo. And for that, I'll invite my colleague, Dr. Alicia Frame, who's Senior Director of Product Management for Graph Data Science. Alicia, welcome.
Okay, I'm so excited to be here for the first live demo I've done in 2.5 years. So we're going to pray to the demo gods. And I'm really thankful that I've got a little box to stand on so you all can see me above the screen. So talking about this, we've told you a lot of amazing stuff about what Neo4j can do, how cool graphs are. But this isn't a tech conference unless we do hands-on keyboard, real demo, proof points that this is something real. So what we're going to do today is, under 10 minutes, I'm going to show you how we can stream data directly into GDS from a BigQuery database using Apache Arrow. After we've built our graph projection, we're going to go ahead and we're going to run a recommendation workflow. We're going to run graph algorithms on this in-memory graph. We're going to save those algorithms back to our database. And then we're going to do some no-code analysis with Bloom. And so the data set we're using today is from the Open Graph benchmarks, and it's actually their scale benchmark data set. So this is a citation graph, authors, papers, and institutions. We're using this because it's publicly available and really big. But you could think about this as any kind of recommendation workflow. It could be customers, products, and stores, anything like that. So in order to show you that there's no secrets behind the curtain, I'm going to start off by running and just proving we don't have anything loaded yet. And now what I'm going to do is I'm going to toggle over here and I'm going to start running our import notebook. And so I'm going to talk through this as it runs. It's pretty fast. What we're doing is we start up by connecting to BigQuery, and then we're using Python to orchestrate all of this. So it's already connected to BigQuery. We've connected to our Neo4j instance, and we've started using Apache Arrow to build up that data structure to load into our in-memory graph. And you can see here that while I was talking, it already finished the node loading. 244 million nodes loaded into the graph in seconds. Once we finish that, it gets better though. Don't clap yet. So once we finish that, we start loading edges. And there are 1.7 billion edges in this data set loading as I talk. This is the slowest part of our demo. It takes a couple seconds. So I'm going to pop over and actually show you what's happening under the hood. So what we're doing is we're using the Arrow API with GDS to take that data from BigQuery, build up an in-memory representation, and start feeding that into the database. We're building up a graph projection, so that's that super performant one. And you can see here that we have functions that start feeding the nodes. When that's completed, we signal that we're done. Then we start feeding the edges. And if I pop back, hopefully we're almost done here. This is a lot of records building really fast and in real time. And if you look at how we're spreading this out, we have 83 different workers processing over 1,300 tasks. And as I spoke, we just finished 1.7 billion relationships loaded into GDS. This is the moment to clap. And so the final step is now we have to signal to Neo4j and GDS that we're done. So that finished, and we can pop back over to browser, and I can show you that now we've got that graph in memory ready to analyze. So next step is it's time to do some data science. In this notebook, we're going to build up a very simple recommendations workflow using our GDS Python client. So the first thing we're going to do is we're going to connect to Neo4j, and we're going to bind that graph that we just created to a Python object. The first thing we're going to do is we're going to run degree centrality. So this algorithm is going to run on that entire in-memory graph, nearly 2 billion objects. And it finished in less time it took me to explain what I was doing. And the next step, this is where we're going to do a little bit of filtering because it would be really boring to watch a minute of node similarity running. So we're going to go ahead and we're going to filter out orphan nodes, because those don't tell us anything. We're here for connected data. And the really dense nodes, because those aren't informative. And we loaded nearly 2 billion records, but for this analysis, we're going to look at papers that have cited each other. So I've cut that in-memory graph down to a smaller graph for my analysis, still not that small. We've got nearly 500,000 nodes, relationships in memory, ready to go. So now we're going to do the recommendation workflow. Step one is a graph embedding. What a graph embedding is we're going to basically create a numerical representation of all that rich interconnected data in our graph, and we're going to add that to every node. And again, finished in less time than it took me to explain it. Now that we've created that representation, we're going to figure out which papers in this graph look like other papers. And so we're going to use k-nearest neighbors. We're going to build up a nearest neighbors graph. And what's really cool about this one is it's approximate. So we don't have to do a brute force comparison of every node to every other node. We still end up doing about 80 million comparisons, though. So now we've added to our in-memory graph, based on those papers and their embeddings, which papers are most similar to each other in order to recommend papers based on a seed paper. So all of this has been saved, and now we're going to go ahead and we're going to dump our graph projection to a new Neo4j database so that we can start looking at it in Bloom. So probably a lot of you have used Bloom before, and it's a live demo, so of course I am logged out. There we go. I'm going to choose my perspective. And the first thing I'm going to do is I'm going to just pull up a citation network. Fine. In order to show you what this looks like. And so Bloom is just going to pull up 1,000 records. We can see papers that it cited each other. We basically get a sense for what this data looks like, right? The red relationships are which paper cited which other papers. And for this, we're going to zoom in to a single paper, which I have created a search phrase for called good paper. So let's go ahead and look at this one paper. And what we want to do is pretend a person has come to your website, they've looked at this one item, and you want to start building up recommendations around it. So I'm going to dismiss the rest of the graph, and I'm going to build up the neighborhood around this node using a scene action. And so this uses breadth first search in GDS to build up the neighborhood around this node. And I can see here's my node of interest. Here are those similar to relationships we just derived. And we can see the citation relationships. So we've built up new information. And now we can start data sciencing in real time. And this is where it gets pretty. So we're going to run Louvain, which is a community detection algorithm, to see how this neighborhood clusters. And with a few clicks, didn't have to do anything fancy in Python. I can apply rule-based styling, and this is where you ooh and ah. We've got all of these different communities, real-time, labeled by different colors. And now, okay, someone came in and they read the yellow paper, what do I recommend? I can see different clusters of papers, but maybe now I want to figure out which one is most important. So I'm going to run betweenness centrality, and again, I'm going to add size scaling so we can see it visually in real time. If this is my seed node and I want something more similar to it, I might choose one of the most important nodes in the same community. If I want to recommend something more novel, I might go ahead and apply something in a different community. And so what I showed you in, I think, under 8 minutes is we went from raw data in BigQuery directly into the in-memory graph, 2 billion records. We ran an algorithm workflow in order to come up with recommendations of other papers. We dumped that to a Neo4j database, and then we analyzed that real-time, no code using Bloom. And this is a combination of lots of exciting new features, hot off the press, Apache Arrow debuting this week, the GDS Python client debuted a couple months ago, and Bloom scene styling using data science in the browser, no code, coming later this month. So hopefully all of you enjoyed kind of the hands-on keyboard demo, and I'm going to hand it back to Phillip to do the next section.
How amazing was that? Thank you, Alicia. That's just spectacular. My phrase for the day is, it ran in less time than it took me to explain it. So what did we just see? We saw Neo4j GDS 2.1 with Arrow demo with 1.7 billion relationships, 244 million nodes, streamed in from Google BigQuery, straight into the in-memory graph at around 30 million relationships per second. And then you saw the Jupyter Notebook, you saw Bloom, you saw running algorithms from Bloom. That last part will be available later this month. So amazing stuff. Thanks again. I'm going to drill into some of the new enterprise capabilities. I talked about these earlier. Compliance is an important thing that large companies look to as a way to certify that the things a vendor says and needs to do are validated by a third party. And we're proud last year to have gotten our ISO 27001 certification. And this depends not just on product features or platform features, but on processes and how we actually operate as an R&D organization and a support organization. We just received our SOC 2 Type 1 certification, and we'll have SOC 2 Type 2 before the end of the year, and then we'll just keep on going with more certifications. If I drill into the product side of this, I've got a number of different pillars here. So AuraDB Enterprise, as well as soon AuraDS Enterprise, run inside of a dedicated VPC. All the traffic is encrypted, including intra-cluster. The data is encrypted. We just released single sign-on not too long ago in AuraDB Enterprise. Just got VPC private link, so VPC peering for AWS added to the platform, and we'll have that added for GCP soon, and much more. And you also get the great core security features of the database that come along for the ride, like role-based access control and schema, fine-grained schema controls. There are a few ways that you know of today to get data into and out of Neo4j. One is the Kafka connector, and then another is Neo4j connector for Apache Spark, and then there's the BI connector. We're announcing 2 new connectors this week. One you just saw in action, which is going to run with GDS, starting with version 2.1. And then we're also releasing, actually released today, a new data warehouse connector. So this works in the same way as our Spark connector, where you connect to a Spark job inside of your cloud data warehouse of choice, and you can pull data in to Neo4j. So trying to make it easier to connect to more platforms. Speaking of making it easier, for years, we've been focused on building capable sound infrastructure and tools to make development easier and to back your applications. But if you're responsible for administering Neo4j, it can be a little hard to know where to start when you're tasked with managing a database. I've been looking forward to announcing an ops management product for years, and I'm really happy to be able to talk about our plans for one today. So this is going to be called Neo4j Ops Manager. You can see at the top you'll be able to manage all of your Neo4j deployments centrally. So this is a bird's eye view of the cluster, along with all the different roles and status of machines in your cluster. You'll also see a number of dashboards on the left, so covering key OS stats and JVM stats and information about different databases and what's running and how it's affecting the system. And then there are specialized UIs for different things that can get very complicated over time. So for example, access controls can get really complicated, and we're developing some UIs to make it easy to administer roles and permissions. And I'm pleased to say that Neo4j Ops Manager will be available later this month. Ops Manager will start out for self-managed where it's needed the most. Aura, there's some overlap with Aura, and as the year moves on, we're going to integrate some of what we've got in Ops Manager into Aura. All right, transitioning on to frictionless experience, just making things easier and better for all of you, especially for new users. In Alicia's demo, you saw graph algorithms being launched directly from Bloom. So this was a preview version she was using. Seems to work pretty well in my book. And the good news is this will be available to all GDS users in Bloom later this month. The next is for those of you who have been in Aura recently, you probably saw our early access of a new tool that we've just started getting out there called Neo4j Importer. This is really aimed at helping especially new users who aren't familiar with the graph, who have data lying around, typically in CSVs or in something that can get to a CSV. And how do I get my data in? I need to model it, and then I need to move data across. And this tool will do all of that for you visually. So it's small to medium volumes, Aura only currently, but we're pretty happy to have this, and we've just been evolving it, and this is going to move from early access to GA, and you'll start seeing it roll out in more places. Another library that we launched just about a year ago is GraphQL. So we have a whole framework for running GraphQL with Neo4j. And if you look at the history of this, when GraphQL started coming out of Facebook, we looked at it and said, all right, there's no reason why Neo4j can't be a great database, if not the best database, to back a GraphQL-based application. And I think all of you who are developers know what GraphQL is. I think of it as like a next-generation REST API. So it's not a database query language. It's really an API. So our GraphQL library lets you natively support GraphQL. It does translation into Cypher, just makes it really easy from a low-code perspective. Even though this is quite new, it's starting to make its way into your applications. And we were checking just a few days ago in preparation for the keynote and saw that nearly 1 billion GraphQL queries had already been run in Aura, and this number is just going up like that. There's more coming here. We're going to keep improving the library itself, but this obviously begs for a UI, so it's going to have a UI, and it's going to look something like this. You're going to see that later this year. Another thing we recently released, this is back to April, but quite new for GDS users, is where do data scientists live in all day? In Python notebooks in Python. And so we created a new Python wrapper that actually makes it possible for you to just call graph algorithms using Python, make it easier to call Cypher. So really full Pythonic support for GDS. And you saw some of this in action in Alicia's demo. And the last thing I want to talk about today is Neo4j Workspace. As we've added more and more tools over time, you've ended up with more capabilities, but it's also more UIs to learn and to operate. And this is probably fine if you're an advanced user, but if you're a new or a casual user, it can be a lot to get your head around. So for that reason, we're excited to announce a new unified developer experience. And you can see 3 tabs here. Actually, you probably can't see 3 tabs here, but I'll tell you what they say. There's Explore, Query, and Import. So Query is a lot of the core features from Neo4j Browser that let you write queries, return the results. Explorer takes in a lot of the key features from Bloom. So you can just shift back and forth from one to the other. And then Import brings in the data importer capability. So this is going to keep improving, and you'll start to see more here. We're just about to enter early access today. So neo4j.com/workspace, in case you'd like to go out there and sign up for early access. That'll be rolling out in the next few weeks. So expect to eventually see this roll out starting in Aura, and hopefully this will make the experience easier for all of you. So I think we just learned that demos are worth 1,000 pictures if a picture is worth 1,000 words. So to demo Neo4j Workspace, Importer, and more, I'd like to invite the one and only inimitable Michael Hunger to the stage.
Hello, everyone. Thank you, Phillip. I'm really, really happy to be back and see you all in person, and it's such a great time at GraphConnect here. It's like in the old days. So really happy to show you Workspace today. If you know me, then you know that I really care about making the experience and life easier for existing and new Neo4j users, and that's why I'm really, really excited that we've worked in the last few months on this new experience that makes it so much better for people with no code to get from zero to results in really short times. So what I want to show you today is how we take anonymized registrant data for GraphConnect and use Neo4j Workspace to get it into the graph with no code in under 5 minutes. And yeah, let's go and let's see how this goes. So to start out with, we just create an ORDB free instance. So I just selected ORDB free here, gave it a name GraphConnect attendees, chose a region close to us and an empty database. And I basically just say create instance. It will create this instance, and I need to take care of the credentials. And while the instance is spinning up, I want to show you the data set. So we took registration data, but anonymized it with IKEA product names. So if you see the first name and last name, Swedish is IKEA product name, so you're sure that there's no personal data in here. We generate fake company names as well, but there's information about roles, states, industries, job functions in here. We also have data sets on expertise, so like data visualization, full stack development, and so on, and use cases. So what are you using Neo4j for? So these 3 CSV files we want to get into Neo4j. So my instance is running now, and I have my GraphConnect attendees instance running here. And as you can see up here, if you've been to Aura recently, you know that this button usually doesn't say open workspace, it says other things. So this is actually brand new and an opt-in experience. So if you sign up for the EAP, then you can try this out. But this is really built for new Neo4j users, right? So that's to make it easier to get started and have everything in one place, don't have to fiddle around with multiple tools. So if you open Workspace, we basically get to this view where it starts with a blank slate, import, right? So these are the 3 tabs. I hope you can read them from back there. And what we do is basically we add our 3 CSV files here. And so you see all the attributes, first row, and then we can start modeling our data. So Emil talked about, and Jonathan talked about how easy it is to basically take a whiteboard, take a domain, start drawing your graph with your domain experts, and if the data is coming from the domain expert, it becomes even easier. So I can, for instance, start to create my attendee node here. I select a file for mapping attendees. I can select my properties from the file. So I take the first name, last name, job function, and participant ID, and add participant ID as an ID. Then we can drag out, for instance, something like a use case, like this. We might pick the use cases file, select the use case property here, and the ID as well. And then what's missing between the two is the relationship. So it's an has use case. And has use case relationship. So we could flip directions if we wanted to with this arrow up here. And now we use for our mapping file the CSV again. We map from participant ID to use case. And that's how I would model out the whole graph. I don't want to bore you watching me kind of just draw on a whiteboard. That's why you can also, with Data Importer, you can also save your models with the CSV into a file. And I can just load this model in. So I have now my attendee node, the industry, roles, expertise, use cases, but also where are people coming from, which state and which country. And this is all my data mapped. As you also see that my CSVs are now all green, so all the columns in the CSV are actually mapped to the graph. I can modify this if I want to. And then I just click on Run Import. And so in a few seconds, it will import this data into my AuraDB3 database. So you see the results here, so it took 4 seconds. And what's really cool about this result, you can actually see the queries that it used to import the data. So that's actually quite good code to import the data into Neo4j efficiently. So you can also take this code, put it into your application or scripts if you want to do your own loading later on. And then we can actually start working with this data in Neo4j, right? So query, as Phillip said, is kind of the browser tab. So we can, for instance, explore our query in the as a schema visualization. And if you look between import and query, it's basically the same model, right? So whatever we had in the CSV via the modeling live went into Neo4j. And now I can start querying this data as well. For instance, fetching a bunch of attendees and their overlapping industries. Of course, this kind of similarity visualization is OK in browser, and you need to know Cypher. But what we actually wanted to do is we wanted to not write code. So let's hop over to Bloom and look at the data there. So if I start with a state, let's say we are in Texas today. I hope this works. Oh, sorry, it's not name, it's state. Texas. And then from the state, we can go to the attendee. Then, for instance, to the industry. Come on. Industry. Oh. OK, then we go to the attendee first. And Bloom does not like me right now. OK, let's see. No. OK, so we can probably refresh our perspective so that Bloom also knows that we got the data in. So Workspace is preview alpha, so it's not 100% integrated, but I think I lost some network connection or something like that. Yeah. Anyway, so browser can connect, Bloom can't connect, but let's refresh this and see if we can now fetch our attendees. No. OK, demo gods were not as helpful with me as with Alicia, so sorry for that. Yeah, we use our luck. But anyway, so you can imagine when I create this data in Bloom, then I would kind of get the no-code visualization out of that. So I really love this approach where it's all unified in one surface. People don't have to go around, search for tools, but it can go from import to visualization to query in one go. And then if you want to go further, then you can, as Phillip said, go into building your GraphQL API without writing actual code because it derives the type system, type definitions from your data in the graph. And then you're basically from 0 to API in 5 minutes without having to do anything basically manually as such. So from that perspective, if you want to learn more about all these tools that we've seen today, come to the sessions later today and tomorrow. And with that, I want to welcome Emil back on stage to close us off.
Your turn. All right, 50% hit rate on demos. I think that proves we're doing this live. Like, I think the trick when you have demos and it fails, you should always blame the network, right? But here at GraphConnect, that's actually a graph problem, right? Like figuring out, so we can't really blame the network, because that means we haven't understood the graph completely. Wow, look, I was there when we made the plans to build this stuff. I've been seeing it piecemeal coming in. I've seen dry runs of this presentation, by the way, with a working demo by Michael. Yeah. Still, just seeing all of this, I don't know what you thought. I thought that was absolutely amazing. There's a lot of amazing technology right there. And as I think about this, as I reflect on this, I think there's kind of two, the secret sauce here, if you will. I think there's two components to it. One is Neo4j now has the biggest engineering team dedicated to graph technology on the planet. The biggest. Bigger even than the Googles and the Metas, et cetera, of the world, all fully focused, dedicated to just moving this product suite forward. So that's a huge part of it. The second one, though, is a couple of secret sauces in the architecture of how we've built out our platform. And I thought I'd unpack that a little bit for you. It may not be obvious when you look at it from the outside. The first one is we have a kernel that can serve up both transactional and analytical workload. Did you see this in the presentation and the demo? And that's actually the holy grail of databases, right? Being able to do this. There's a clear trade-off between transactional and analytical workload. But we have one unified graph-native kernel that can do both. It's the only one in the industry. And I'm not talking this bullshit multi-model, add a layer on top, lipstick on a pig. This is truly graph-native, transactional and analytical workloads out of the same unified kernel. That's amazing, right? So that's one part. And then the second part is this in-memory projection that GDS runs off of, right? Which is this super compact, compressed, in-memory version of all or part of the graph, depending on what you want for your algorithms. Paired up with these highly specialized, optimized, deeply parallelized algorithms running on top of that in-memory graph projection, which then can spit out results in form of graph algorithm results like you saw with Bloom that made the nodes be bigger or smaller in the demo that worked, that Bloom part, right? Or in the form of graph embeddings that then can be used by your normal machine learning pipeline, right? This all running in one unified system. So that's the second one. And then the third one is that I think we have the richest set of tools and integrations wrapped around this platform that exists today in the industry. And you saw many of them in the demos here today, and Phillip alluded to others like Ops Manager. And then we've invested a huge amount in security over the last several years, which is deeply relevant if you're building any kind of a cloud-native application or really probably any deployment inside of the enterprise. And this is becoming even more relevant as we're shifting into the cloud with Aura, right? And so these are things like SSO integration, single sign-on, private link, VPC, peering, graph-native role-based access control, right? Things like that. And then the fifth one, all of this technology runs wherever you want it to run. It can run in your own data center, self-managed, in hybrid deployment, and of course through Aura on the public clouds. So you add all those things together, and that's the kind of stuff combined with the 300+ person engineering team growing rapidly that can make the magic that you just saw Phillip and team present. Cool, so that was that. Now we've talked a little bit about what was going on inside of the engine room and what we've built. Now we're going to switch gears, and we're going to talk about what's coming next. What's up in the graph world over the next several years. I think of this and talk about this as the long arc of the graph. And the way that it makes sense in my head is to think of it in these two broad buckets: operational systems, so developers building applications, the database is a system of record, the backend for that application. And then data science and analytics, so data scientists using the data in the graph to predict the future, right? Those are the two broad things. And if I start on the operational side, and I think about what's happened, I took a screenshot from the last GraphConnect, the use cases. These were the top 6 use cases that we talked about back then. Today, from earlier, just a few slides ago, whatever, here are now the use cases. And you can see how they've expanded, they've grown in these past 3-4 years. This trend, I predict, will continue. And why? Because I think the secular shift, the secular trend behind what we're doing is something like the following. The world is becoming increasingly connected. That's hardly a controversial statement. We all feel this, how everything is becoming more intertwined in the real world. Well, if that happens, hardly a controversial statement, but a little bit more subtle than that is, what are the consequences for data? And when you think about data, we're all data people here. But actually, what is data? Right? You start thinking about that, like, what is the definition of data, right? Well, data to me is the digital representation of the real world, right? It's a way of describing the world. So as the world is becoming more connected, then data is becoming more connected. There's going to be more relationships expressed in data. There's going to be more foreign keys in your relational database, that type of a thing, right? More and more every day. And then as a consequence of that, there's going to be more and more use cases where you really either benefit from or have to use a graph database to be able to solve your problems. And so that, I think, is the secular wind behind our backs that is just going to cause this explosion of use cases, more and more every time. When I hopefully see all of you come back a year from now, right? There's going to be another slide, and there's going to be even more use cases on that slide. So I believe that's going to continue. And in fact, I researched this a little bit, and I went to Wikipedia, and I looked at the article for domain model as a way to, how do you express a use case? How do you express an application? It's in your domain model. And the Wikipedia article for domain model, there's a picture. And it's probably too small for you to see, but it doesn't matter. It's a healthcare system. It has patients, it has doctors, it has providers. When I show this in Europe, my joke is, you can tell that it's a US healthcare system because it's really complex. And you look at that domain model, and even in the Wikipedia article for a domain model, what strikes out to you? Well, that's a graph, actually, right? And then, as I start thinking about it, do I know any domain out there, any application out there, where the domain model actually is not a graph? I went to Google Images. Pull that up on your phone, go to Google Images, and you search. Actually, I'll show you that later. I'll cue that one up later, actually. First, before that, though, before you go to Google Images, don't do it now. Wait for it later. If you have this domain model and you want to represent that domain model, the canonical example from Wikipedia in a database, right? It looks like this. And then you translate that into a relational database, which is entirely doable. It's actually been mathematically proven that you can take any data and you can represent it in a relational database. You break it down into tables. You have foreign keys for all the lines and all that good stuff. It's doable. It's a little bit awkward, but doable. If you move to a document model, which is great for a lot of different things, right? What you're going to end up doing is that's also very doable. But every single time there's a line in there, there's a connection, there's a relationship, you have to manually encode that. This is definitely too small, but what you see over there is one of the IDs are hard-coded over in the provider, right? And you have to hard-code that as a value in the variable, right? Which is kind of doable, but the reality is that you're trying to implement a foreign key without the support of the database. Right? So your application has to maintain that. That kind of sucks, right? Like the relational database in this case is better than the document database at maintaining this. And then, of course, in the graph world, what ends up happening here is that every single artifact you see in that domain model, there's a one-to-one relationship in the graph model, right? So all of a sudden, you can take this domain model, and it's a one-to-one fit in the property graph model. This is not true for any of these other models. And this is the canonical Wikipedia example for a domain model. And here then we come to the punchline around the Google image search. So I thought about that, like, is there any domain model that isn't a graph? And I went to Google Images and I searched for domain model. And this is just the first one of them. It is page after page after page of graphs, right? So in fact, hit me up afterwards. Can you think of any domain model that actually isn't a graph? I actually can't. So I think the long arc here is that over time, more and more applications, more and more use cases will be a better fit for graph databases. That's the long arc on the operational side. On the data science and analytics side, I'm going to take you back 10 years to this very stage. Well, metaphorically, we were in San Francisco. 10 years ago today, no, 10 years ago, we had the first ever GraphConnect, actually. So this is our decade-versary or something like this. And this gentleman over here is a professor at UCSD called James Fowler, Professor Fowler. And he wrote a book called Connected back in 2012. And he was the first external researcher to get access to the Facebook social graph. And he used that one to prove out some really, really interesting things. He proved out that in two universes, one universe is he knows everything about Emil Eifrem. He knows age, height, weight, shoe size, medical history, diet, everything about me, right? That's one universe. The other universe, I'm a blank note. He knows nothing about me, not even gender, absolutely nothing, right? But he knows the graph. And what he proved out in his book, and he documented, was that in that second universe, when he knows nothing about me, but he knows the graph, he'll be able to, with a much higher degree of predictability, he can predict whether I'm a smoker or a non-smoker, and two, 2012 was an election year, whether I was going to turn out for the election or not. So that's a really fascinating discovery, the fact that relationships are such a predictive part of data. So this is us 10 years ago, looking identical to today. And him stating the fact that actually, it turns out with relationships, you can predict better if you know the graph than even if you know the information on that individual themselves. So that's the core foundation of what we're doing with graph data science. And today, actually, or last year, 2021, 50% of Gartner inquiries on the topic of AI involve some kind of discussion of graph technology, right? So it's becoming a massively popular way to do predictions. And this is not, just a theoretical thing. It exists in the real world. There's a demo out there with actual real anonymized customer data set where we proved out with GDS and fraud detection that we could capture 87% more fraud risks using relationships between transactions. So this one is available. It's a data set, and you can download it. There's also a blog post actually it's a series of blog posts that you can read about it. So if I think about this power, how is this going to be deployed inside of the enterprise, right? Well, I think in single projects, it's very easy, right? Because you pull in GDS, and one of the power of GDS is the fact that it's so easy to get up and running with, especially if you already have data in Neo4j. Bam, you add the GDS library to it, and off you go, right? So that's really powerful. And then maybe there's a second project where you do the same, like you take Neo4j, maybe you integrate some data from some other systems, right? Maybe it's the same systems that you used in the previous one. It's a little bit of duplicated effort, but it's doable, right? But then after a while, it's like you start adding more of these systems, and you start realizing that, wait, why are we doing this effort all over again? And it's typically not always the same team, right? It might be different teams doing it, right? But why are we doing this all over again, where we're taking data out of our BigQuery in that example, or our Snowflake, or our data lake, and we move it into the graph, express it as a graph, and then we can get all the value of the graph, right? Why do we keep doing this over and over again? And what we've heard and what we're starting to hear from forward-leaning customers right now, big enterprises, is that, you know what? What if there was an architecture where we could store hundreds, if not thousands, of disparate data sets represented as a graph that we can then serve up to these multiple use cases to use for data science and analytics? And it should come as no surprise to you that we've actually been building towards this for a while. And several of the things that Phillip articulated in his session just a while ago actually are key enabling factors for this. We talked about the autonomous cluster platform so that we can scale up and down very easily our big clusters. We talked about massive ingest. In fact, Alicia demoed that. And the graph native security architecture, which if we're going to do an enterprise-wide offering, that becomes really, really important. We call this the knowledge lake architecture. And what it is an enterprise-wide, scale-out architecture, a repository where you take a subset, a curated subset of your organization's data. It's not like a data lake where you just throw all the data in there. You take a curated subset, enough so that you can build a graph of your business, right? Represented as a graph. And then you can serve that up to multiple projects downstream. This is, I think, where several big enterprises are going to go over the next several years. I think we're going to see a few of them emerging this year, a few of them next year. And over time, I think that's going to be a very common deployment model. In fact, I believe it's going to be as prevalent inside of the enterprise as the data lake houses and the cloud data warehouses. So if I then try to wrap us all up here, the long arc of the graph, where is our industry going over the next 3 or 5 or 7, many, many years? So I believe that most, if not all applications over the long term will be a better fit for a graph database. I think that's going to happen. Every year there's going to be more and more of them. And I think that most, if not all, machine learning models will use relationships. Also more and more every single year. And in so many ways, I feel like the previous decade for us was getting a lot of the foundational building blocks in place. And this really is our decade to shine. And all of you in here are early adopters and early visionaries. You saw this before most other people saw this. And I think it's going to be a super, super exciting future for all of us graph people. So as I wrap us up here, I want to end on a note which is really my only direction to you all for the rest of the conference. And you've heard a lot of stuff here today. But maybe the most important thing I'm going to tell you right now. So I know this is long, it's morning, it's a dark room. If there's anything you should pay attention to, it's this, which is we're all graph people, right? And what is it that defines graph people? What do we value? Relationships, right? What do we value? Oh, come on. What do we value? I didn't hear you. What do we value? That's right. Could we be more cult-like, right? We value relationships, right? And so use that at the conference. Over the next 48 hours, you can find the content elsewhere, right? You're here face-to-face. Strike up those conversations. You have an amazing set of graph expertise in this room, right? You have people who just walked in, you know, whatever, they heard about this a month ago, all the way down to people who've been doing this for 5, 10 years. Strike up those conversations. Form those relationships. And in one word, go out and connect. Have a great conference. Thank you, everyone, so much.